Hello and welcome back to ML with Philip. This video is part 2 of a previous video, which was the RNN tutorial classifying names with a character level recurrent neural network. And this is an extra optional video where I dive into some additional topics which are very useful to know, but they aren't essential for building RNNs. But I do encourage you to watch this video if you want to get an even deeper understanding. In the first video, we went through the theory of how an RNN works under the hood, and we went through the code to build an RNN step by step. In this second video, I want to cover several topics. The main topic that we're going to cover is we're going to take our RNN that we wrote ourselves, and we're actually going to replace it with Pytorch's RNN class that they've already provided for us in their library. And the reason that we want to do this is because as you progress through your machine learning journey, as you continue to do machine learning, you are typically not going to be writing all of the code for every implementation from scratch. You're going to be using classes and functions from libraries such as Pytorch that have already built a lot of this functionality for you, and they have been done by a team of experts, created it in a fully optimized way. So that's what we want to do here, is we want to use Pytorch's class instead of the one that we built ourselves. So in addition to this, I also want to show you how in our code, we actually had a loop that went through each time step and passed it through the RNN step by step. RNN class in Pytorch, you can actually just pass in the time dimension and it will handle that process of processing the inputs step by step. So we can actually simplify our implementation using that. I want to finish up with showing you how to, instead of use an RNN, use a more sophisticated version of an RNN called a GRU, which is a Gated Recurrent Unit. And then on top of that, I also want to show you how to use an LSTM, which is a long short-term memory. That's the outline for what we're going to cover today. So if you're interested in that, then I'm happy to have you, and let's get on to the video. One thing that I want to mention before we start the actual coding is that we're going to cover using a GRU and an LSTM in this video. However, I'm not going to go into the theory of how GRUs and LSTMs work. I do encourage you to, once we reach that stage in the video, to read up on the theory and try and understand how they actually work beneath the hood. Without further ado, let's get started. All right, guys, this is going to be a great video. I'm looking forward to it. So let's get to coding. So as I mentioned in the introduction, I'm going to start with the code, the exact same notebook that we completed in the first video. And from here, what we want to do is we have this RNN class that we defined. And in the class, we wrote this code to basically do the calculations that an RNN would do. Now, what we want to do instead is we want to replace this code with the RNN class from, let me just run everything up to this point. We want to use the RNN class. So it always helps to take a look at the documentation so that we can understand how to use this class. So let's go ahead and do that. So this is the documentation for the RNN class. As you can see, it will take in a similar set of inputs, and it will output a similar set of outputs that we have already been doing in our implementation. It takes in an input and a hidden state, and it outputs an output and a hidden state. Now, the input has to have these dimensions. So it needs to have a dimension L of the sequence length and the dimension H, which is the hidden shape. Now, because in our implementation, but we only required one dimension, and the dimension of our input was actually the length of our vocabulary. In this case, we need an extra dimension here. So we're going to have to make that change in our code. And the output is also going to have this dimension, this additional dimension here. So we're going to need to account for that in our output as well. So it definitely helps to look at the documentation to understand what kind of inputs it expects and how to properly define this class. If we look at our original RNN class and we consider a random example. So we're just going to pick a random example. And in order to pass it through our neural network, well, we need to use this code here. And we also want to do this. Okay. So if you recall, we use this code, and what this code does is it takes we have a language and we have a name, and this encodes it into an input and a target tensor. So the input is our encoded name, and it has this shape, and our target is our encoded language, and it's just a single value. Okay, and we need to iterate through the first dimension of this sequence, the time dimension, and we need to pass in the input step by step. So what we do is we would take the input at the first dimension, and we would also need to create a hidden input, which is just a bunch of zeros. Okay, and then we get an output, and we get a new hidden. Okay, and then we would repeat this process for the first time step, second time step, so on and so forth. That's our current setup. Now, what we want to do is we want to get rid of these. We want to replace these with the nn.rnn class. So we want this to be nn.rnn. And nn.rnn requires the input size and the hidden size. So the input size is going to be our input size, and the hidden size is going to be our hidden size. Okay, and we don't have to actually combine or concatenate our input and our hidden if we use the RNN, because it's actually going to take care of that for us. So we're no longer going to need these two linear layers, because we're going to just use the RNN class, which does those computations for us. And we no longer need to combine the input and the hidden either. So let's still print some of these shapes. Okay, so let's start with this. Let's try and call the RNN class. So remember, our self.rnn is going to take in an input and a hidden. So it's going to take in the input and the hidden, and it's going to output the output and a hidden. Okay. So when we call the RNN class, this is how it should look like. So that's good. We no longer are going to need this, and we no longer will need this, and we no longer will need that. Okay, good. So, okay, so we have this. Now, as I mentioned before, when you look at the documentation, there's actually an additional dimension here, the sequence length dimension, which we don't have right now because we just pass in the row at that time step. So we're actually going to get an error if we try to call this new RNN class that we defined. But let's try it anyways and see what happens. Okay, so as expected, we got an error that the dimensions don't match up. So what do we need to change here? Well, if you look at the input that we actually pass in, input at a time step, if we look at that, it actually has a shape of, it's actually one-dimensional. It has the shape of the dimensionality of the input. However, it doesn't have a shape for, it doesn't have an additional dimension for the length of the sequence. Now for us, because we're actually passing in the time steps one at a time, so we actually don't need that dimension. However, the RNN class requires that dimension. So even though we don't need that dimension, we still are going to have to add that dimension in order to ensure that the code works. And we can use this unsqueeze function, which adds an additional dimension in the specified index. So if we do that, we actually, everything stays the same, we just have an additional dimension. So let's do that. So our input at time step t is, input, we're using the first time step, and then we unsqueeze it. So now we have the appropriate dimension. Our hidden state as well, it is going to need to have an additional extra dimension here. So we will just make this adjustment. And now when we do this, sorry, we need to do that. Now when we do this, everything is actually going to work. We're going to be able to input it into the RNN, and you can see that our input has a shape of 157 and our hidden has a shape of 128. So we've added that extra dimension. Okay, so sometimes functions in Pytorch require specific dimensionality, and even if you don't use that dimension, you still have to match that dimensionality to ensure that everything works. So we can actually make this a little bit simpler. Instead of having to add the dimension, we can actually modify our name to tensor function. So our current name to tensor function, it will give us a two-dimensional input, right? And When we select a time step along the first dimension, well, we lose that dimension. So what we can do to ensure that things work is we can actually just add an additional dimension here, and then we just index into that new dimension. So now when we index into our first dimension, which is the time step, we will have a two-dimensional vector. So if we make this change, it's actually going to fix our dimensionality problem for us. So let me try that now. So I'm going to remove this extra code that I used to fix the dimensionality. And I'm also going to actually start using the init hidden function, and I'm going to just make the adjustment there. So let's use our init hidden. Okay, now, and we're also going to have to fix the target. Likely, we're going to have to fix the target to line up the dimensions, but let's leave that for now. Let's just run our code as is and see what happens. Okay, everything ran with no errors, and we got an output and we got a hidden. Okay. Now our output is all zeros, and it has a shape of 128. So that is not good. Okay, our output that we want needs to have a shape of the number of languages. So let's fix that as well. Let's remove the softmax for now, because we'll get to that later. Okay. So we're able to pass in an input and a hidden state to the RNN class, and it returns an output and a hidden state as expected. However, if you look at the RNN class, the output that it returns, its dimensionality is going to be the same as the hidden dimension. So the output has the same dimensionality as the hidden size. Okay, that's how the RNN class works. But for our purposes, we want an output that is going to that we're going to turn into a probability for how likely we believe that a name belongs to each given language. So we're actually going to need an additional linear layer to make the dimensions work. So let's remove these two. Let's create a new linear layer. And what it does is it takes the output and it just kind of transforms it into the proper dimension. So what's a good thing to call this? I'm just call it output to output, or just self.linear. If I can't think of a descriptive name, I'm just going to call it self.linear, but if you feel like there's a different name that helps you understand it better, feel free to call it whatever you want. And as we mentioned, the output from the RNN is going to have a dimensionality of the hidden size. So what we want is the input dimension to be the hidden size, and the output dimension is going to be the output size. Okay, so let's get rid of these now, and let's go again, and we're gonna try and see if if our output is now the right shape. Okay, so let's take a look. Okay, so our output is definitely the right shape now. It's 18 dimensional, which corresponds to the number of languages that we have. And if we look at our output, so now we want to take the softmax to convert these into log probabilities. Okay, so one thing though is we added an extra dimension to all of our tensors, right? So we have this extra dimension, and so what we actually want is we want to compute the softmax along the second dimension now. So we just change this dimension to 1 instead of 0. Okay, and let's take a look now. And let's do that. Okay, so our output looks like what our output should look like. And our hidden state looks like what our hidden state should look like. So it seems like we've been able to replicate what we had before, but now using the RNN class from Pytorch. Great. So the last piece that we want to verify is that we're calculating our loss correctly using the criterion. So our target, we might have to change the dimensionality of our target as well to make sure that this works. So let's give it a try. We take a look at the NLL loss criterion. So it expects a input like this, an input where C is the number of classes. So it can either come in C or N by C. And you can either come in N or just, no dimension, just a single value. So let's see what happens. We have a target, which is just a single value. We have an output. And our output now has 2 dimensions. So what we actually want is we want our output at the first dimension. Okay. So now let's see if this works. Loss. Okay, so everything works. We just had to index into the first dimension from the output. We've fixed and tweaked all those little dimensionality things to make sure that everything still lines up. And let's now see if we're able to train our RNN. So everything here stays the same. The only thing is that we take the output at 0 because we index into that first dimension. And I believe this should work now, but let's give it a try and see if it actually works. Let's just run everything from the beginning to make sure. So let's run everything from the top. We don't need this anymore. So let's run everything from the top and, sorry, we had to remove the print statements. So let's remove the print statements because we verified that everything works. And now let us run everything. And let's see if we're able to learn. Okay, it looks like the loss is going down, similar to what we had in our implementation from the first video, from the first notebook. So everything looks good. So we'll let that finish running and then we'll come back. All right, guys, so we've let the model train, and now we take a look at the learning curve, and it seems like this model is actually better than the model that we created ourselves. So, that's another advantage of using the built-in Pytorch classes, is that they've tried and tested and built things in a way where it's much better. Everything's been optimized. It has extra functionality and so on. So you can see that our loss looks really good, actually. And now let's predict this. Let's make some predictions and see how our model performs, how our new model performs. So what we need to do is, there's an error, and that is because, if you remember, our output is now two-dimensional, so we have to index into the first dimension of the output. And now we can take a look at the outputs and see how they perform. So you can see that this model is doing much better than our other model. It seems to get most of the languages correct. It seems to make really good predictions. Yeah, pretty impressive. So just from that tweak, we actually gained so much performance from using Pytorch's RNN class. That was the first thing that I wanted to cover in this video, is how to implement an RNN using Pytorch's RNN class and how to change our code accordingly to accommodate for that. Now, the next thing that I want to do is I want to take this RNN class and I want to use its capabilities. So one thing that the RNN class allows for is that you can actually pass in the time as an additional dimension instead of having to pass in the inputs, the time steps one by one, as we have been doing in a for loop. Instead of having this for loop here, we would just pass in the entire input instead of having this for loop here, we would just pass in the entire input. Going back to the documentation for an RNN, you can see that it has this L dimension. That's that additional dimension that we added. Now that L dimension can have the actual time steps in it instead of just having an empty dimension and passing the time steps along one by one. So let's do that. So in order to do that, well, firstly, instead of adding this extra empty dimension, we're just going to remove this dimension that we added because we no longer need it. We're not going to be indexing into the time dimension anymore. We're just going to use that dimension, and we're already going to have a two-dimensional input that we expect. So we no longer need that. Let's run everything to see now what our inputs are going to look like. So if we look at our input, it has a shape of 9 by 57. So it has the length dimension, the sequence length or the time, and it has the dimension of the input size, the number of vocab that we have. Our target is still the same. Our hidden is still going to need that extra dimension because if you look at the RNN documentation, it has this dimension here, which is just 1. So it has this D dimension, which is just 1. Unless we were using a bidirectional RNN, which we're not doing. So our hidden still stays the same. And we'll see that it's still going to be, the vector, the two-dimensional vector where the second dimension has a size of the hidden size. Okay, so now instead of passing in the input at a time step, we just pass in the entire input. And okay, now you'll see that something important changed. Our output before was just a single one of these values because we passed the output, we generated multiple outputs and we took the last one at the last time step. But now, since we've passed in the time dimension, we've passed in all of the data, we actually get multiple outputs, and we get the output at each time step. So you'll see that the output has a shape of 9 because it has an output for each time step. Okay, so that means that we actually have to take the final output. So let's make that code change in our notebook. Okay, so we go here and we calculate a bunch of outputs, correct? And instead of getting one output now, we're actually going to be getting multiple outputs for each time step. So what we want is we actually want the output at the last time step. So take the output at the last time step. Okay, and then we're going to pass that output into our linear layer. Okay, and when we do that, we should get the correct dimensionality and output that we want. So let's give this a try now and see if we do get that. Sorry, we don't want to take the output at 0. We actually want to take the output at -1. Okay, so we do this. And now I believe everything should work. Okay, and it seems to be working. We no longer need output at 0. We can just take the output because we've already indexed into that dimension. Okay, everything looks good, so I'm happy with this. Let's see how our results look. So let's just fix anything here. We no longer need to loop through the time dimension. We can just go and do this. We no longer have to index into the output, and this should just work. So let's see if it does. Okay, everything is working. Let's check back in a couple of minutes to see what our loss looks like. Our neural network has finished training, and let's take a look at the learning curve now. So yeah, looks like we got a similar result as before, but now we were able to pass in the entire sequence at once instead of iterating through the time dimension ourselves. So pretty neat. I thought that was very useful, and especially if you're writing neural network, instead of having all of this extra code to iterate through the time step, to write in the linear layers yourself, now we just, as you can see, we just pass in our input to the RNN, we get our output, and that's it. And in our RNN, we just have an RNN plus an additional linear layer and a softmax. We don't have those other layers that we had before to do all of the calculations within the RNN. So that was the next thing that I wanted to show you guys, is how to pass in the entire sequence at once into the RNN. The next thing that I would love to show you guys is how to replace this RNN with a GRU. Now, a GRU is called a Gated Recurrent Unit, and it is a more sophisticated RNN. So the GRUs have two mechanisms called an update gate and a reset gate. And the update gate is responsible for basically determining whether or not we want to remember or forget the extra information that we've picked up in the hidden state at the current time step. Do we want to update our hidden state, or do we want to not update it? And the reset gate kind of functions as a mechanism to clear the memory, basically, and say, do we want to remember our hidden state at all, or do we just want to start fresh at the current time step? So there's a lot more theory to it. I'm not going to go through it here. I encourage you to read up on GRUs. And then after that, we're also going to create an LSTM, long short-term memory cell. And it works on a similar principle. I'm just going to copy this RNN class so that we have this saved from before. So let's call this class a GRU. So I know it's going to be very difficult to create this GRU. What we have to do is we have to replace the letters RNN with the letters GRU, and everything's going to work. So let's do that. Let's go ahead and do that and see if everything does work. And it does. So you can see that a GRU is the same as an RNN. It takes in the same inputs and it outputs the same outputs. So we don't have to change anything. We just have to call the different class. And we can train our neural network now. And let's check back in a couple of minutes and see what the results look like. All right, so we finished training our GRU, and now let's take a look at the results. As you can see, the loss is actually higher than what we had with the RNN. So, I'm not going to get into digging into the results and why the loss is a certain way or optimizing this neural network. I just want to show you how to implement it. The important thing is that we got our GRU to work. And now let's take a look at the LSTM. So let's take a look at the documentation for an LSTM. So the input actually changes. In addition to taking an input and a hidden state, it actually takes a tuple with a hidden state and a cell state. And it also outputs a tuple, which has a hidden state and a cell state. In addition to a hidden state, we also have a cell state. And same way that we defined initialized our hidden state, we're going to initialize the cell state as well, because we have the same dimensions and we initialize it at 0. Sorry, I'm going to call this a new function. I'm going to leave our GRU function as it was so that we have all of the 3 different classes, and I'm going to write the LSTM function. So so as I mentioned, we have a new input, which is the cell state, and we're going to use an LSTM now rather than a GRU. Our RNN, our LSTM now, it expects a hidden and a cell state. Okay, and it is going to return a hidden and a cell state as well. Okay, so that's what we want, and I think everything else should more or less stay the same. So let's run everything. Let's run everything now and see where the error is going to occur. So let's do that. Okay, no error so far. We need to initialize our cell state. You know what we could just use the same function. We don't need to we don't need to copy the same function twice. So let's do that. And we're gonna go like this. Okay, so we also just need to get the cell state in order to get things to work. And now everything should be fine. Okay, everything seems good here. So now let's go ahead and train. Just run everything from the beginning. And let's train our LSTM now. And yes, of course, we need to change our input and our output. And yeah, everything should work now. Okay, so our LSTM is learning now, albeit quite slowly. So let's give it a few minutes, let it finish running, and then we'll check back in. Okay, so our LSTM has finished training. Let's take a look at the curves. Okay, so you can see that the performance was not as good, but I don't want to get stuck on optimizing the RNNs, because that's not the purpose of this video and these tutorials. But one thing I will say is that GRUs and LSTMs have many more parameters. There's many more parameters and calculations that are being performed. This means that it actually might take a longer time to train all of those parameters because of the increased complexity. Another thing I want to note is that we're doing stochastic gradient descent. So we're just taking one example at each time. So it can be quite noisy. And it actually might be better to use a batch of examples. And that might help some of these more complex algorithms to learn better. So those are some things to think about when it comes to the learning and the loss of these different RNNs. So just to recap everything that we've done so far. What we did is we took our initial RNN class that we built ourselves and we replaced it with Pytorch's RNN class. Then we went further. We, instead of processing the inputs and the outputs one time step at a time, we actually process the entire sequence at once and let the RNN do that work for us. Then we used a more sophisticated version of an RNN called a GRU. And after that, we introduced an even more sophisticated version of an RNN called an LSTM. That's everything that I wanted to cover in this bonus part 2 of the first video. If you reached all the way till the end of the video, leave a comment down below letting me know that you made it all the way through. I enjoy making these videos. I hope that you gained something useful from this video. And if you did, please leave a like, subscribe if you want to see more videos like this, and check out my channel. I have more machine learning videos, and I will be creating many more machine learning videos and tutorials that I think will be interesting to you. So once again, thanks for watching, and until next time. Bye.